Okay, so we talked in a previous conversation about isomers, and this term surely is new to you. So let's go back and say, remember that one kind of isomers, the first kind we talked about were constitutional isomers, right? And constitutional isomers looked like, what did they look like? Let's go to black, carbon, carbon, oxygen, or carbon, oxygen, carbon, right? Got hydrogens on there, right? Okay. So ethanol, if those are hydrogens, or dimethyl ether, right? Those are constitutional way that things are connected differently. The next isomer that we talked about more recently was stereoisomers. And in stereoisomers, we talked about they have the same connectivity, right? But they're oriented differently with respect to each other. And so that's really what this chapter is about. Stereoisomers are really weird. You need a model set for this. I hope you'll get your model set out as you're listening to this. All right, so first of all, stereoisomers exhibit cis-trans isomerism, and the example we saw of that, one example we saw of that was like Cl and Cl and H, right? And so there's a double bond here. So the chlorines are on the same side of that double bond, they're stuck there, right? That's cis-trans isomerism. Or if the chlorine was on the other side, it would be tran, right? That's cis-trans isomerism, and rings are another way to keep bonds from being able to rotate completely, right? Now, there are other kinds of isomers, stereoisomers, that we're concerned about. I would say more commonly, we're going to be more concerned about stereoisomers that have a chiral center, all right? And what does chiral mean? A chiral object is asymmetric, and this is not actually a chemistry term. This is a geometry term. Chiral means it's asymmetric, which means it is not the same as its mirror image, right? And the classic example for this it's given is like two hands, right? You've got a right hand and a left hand, you know? And actually, I got those backwards tonight. A right hand and a left hand and a right hand. So if you turn this guy around 180 degrees, it's not the same thing, right? You cannot superimpose one hand on top of another. If you turn this hand around, suppose if this is the back of the hand, let's draw some hairs in there. Guys, got hairy knuckles. Okay? If you turn this around, then all of a sudden, you don't, this left hand here, you turn it around, you don't have hairy knuckles, you got a palm, right? So a right hand and a left hand are not superimposable. They are said to be asymmetric, or they are said to be chiral, right? And the classic test for this, of course, is you test. You put things like I just did with the hand. You see if two things are superimposable. All right, so chirality is very important in molecules because I would say biology mostly. Biology, the biological systems, they're 3D, right? And so if you get a molecule, molecules approach each other in 3 dimensions. And so if you get something that's chiral, it turns out that it may be that you might have an enzyme that can recognize the right hand but not the left hand, just like a glove, right? A glove would be a great example of an enzyme where it takes in a molecule, which we're going to call a hand, and you might imagine if you've got a left-handed glove and then you've got a bunch of right hands in solution, the right hands are not going to work with the left-handed glove if the glove is built right or whatever, okay? So because of that, many of the enzymes in your body are chiral, or at least the active sites are chiral. And so this has become very important. Now, I do want to tell you, visualizing these mirror images is very difficult. It's an extremely unusual person. You shouldn't plan on it. Do not plan on being the person who can do this without a model set. It is absolutely critical that you use handmade or handheld models as visual aids. Let me give an example of a chiral molecule. And by the way, it's always going to be some atom, often carbon, with 4 unique things coming off of it: red, white, green, and blue, right? And if you've got 4 unique things coming, X, Y, Z, and I'm down to the end of the alphabet. Let's go back up. A, X, Y, Z, and A. Those are 4 distinct substituents, right? And if it's 4 distinct substituents, then you know that that carbon right there is chiral. Now, how do we know? Well, build one. You need to build one now. Okay, you build one, then you build another one that looks like this one. Then take this guy and turn it around and see if you can superimpose it. And you'll find that you cannot superimpose that. They are not the same molecule. Okay? So do that with a handheld model. Prove it to yourself. And you're going to have to do it a few times, I think, before your eyes get really used to it. I have been doing this, obviously, for decades. And now, whenever I see a carbon with 4 unique things coming off of it, immediately I know it's chiral. All right? So when an atom like carbon forms a tetrahedral center, I said this in the previous slide, it has 4 separate groups attached to it. It's called a chirality center. Okay? That's a chiral center. Look at the attachments below and see if you can identify which carbons have a chiral center. All right? Can you see here that there's a hydrogen here, right? You know the rules for line bond structures. There must be a hydrogen there. So I got a methyl group here, a hydrogen here, a chlorine here, and I need another shape. And an ethyl group here. Look at that. That carbon's got 4 things off of it. Circle, square, triangle, and hairball, right? What about this? Don't forget there's a hydrogen here, right? So I've got circle, square, triangle, and hairball. And all 4 of those are different. So that is a chiral center, right? Now look at this. Here is another hydrogen, right? Circle, square, aha. This is a carbon, and that's also a carbon. However, they're different, right? These 2 carbons are definitely different. So because this one's sp3 hybridized, that's sp2 hybridized. Even if they weren't sp3 hybridized and sp2 hybridized, we could look further away and see if those groups were different. In fact, when this carbon looks to the right and to the left, it does not see the same things. So I'm going to put, let's see, triangle over here and hairball over here and go, yeah, wow, that carbon is also a chiral carbon. Okay? You should do this with model sets, but your eyes are going to get used to it. If you do it enough, your eyes are going to get used to it. It's going to be very easy. Okay? Now, how many chiral centers do you see in each of the following compounds? Pause the video now and see if you can detect it. It's important for you to practice this in stages. Pause the video now and see if you can detect. Okay, so I'm going to assume that you paused it and that you were playing fairly. All right, I'm going to come over here and I'm going to say, well, there's a hydrogen, circle, oops, that's not a circle, that's a square, square, circle, and whoa, looks like if I go both ways, this looks the same as that, triangle and triangle, right, because it's symmetric. So this is not chiral. What about this one? Here's a hydrogen, right, square, circle, triangle. Oh, look over on that side. That is not a triangle, right? It's not the same thing. So this is chiral. What about this one? There's a hydrogen here, right? Square, circle, triangle, and hairball. So this is definitely a chiral center, right? Let's do another one. What about this? You know what? This is, I can see. I'm going to let you, this is also a chiral center because this must have a hydrogen coming out front, right? There's a wedge not shown. There's a hydrogen. So this is square, circle. The notes become obviously pretty confusing at some point, right? Because I'm writing all over this. Another chiral center, and there's another chiral center. This one has 3 chiral centers in it. This one has 2, because this is chiral, and this is also chiral. This has none. And what about this one? So I mean, that's got 2 hydrogens, right? There's a lot of centers you can look straight past. This is not one. This has got 3 hydrogens. That's not one. This has got 3 hydrogens. That's not one. This has got 3 hydrogens. That's not one. That's not one. These are not technically chiral centers, but you can see we do have some cis-trans isomerism here, right? And this is the chiral center, right? Because there's a hydrogen. This is a methyl group. Okay? So this has got 4 separate groups. There's one right there. It looks like this is one also. Those X's and stars look the same, don't they? Let me do it in a different color. This is a chiral center. This is a chiral center because it's got 4 different groups on it. And those are the only 2. Okay? So there are 2 chiral centers here. 2 here, 0 here, 3 here. All right, good practice, good practice. All right, so now some stereoisomers can also be classified as enantiomers. Enantiomers are 2 molecules that are mirror images but are not superimposable. Therefore, they're not identical, okay? So only a chiral compound can have an enantiomer. And if you want to know what the mirror image is, you just draw it exactly backwards, right? So I'm going to draw that carbon right here. I'm going to draw that carbon right here. So see that? I'm going to draw that carbon right here. I'm going to draw that carbon right here, okay? And this one was that one. It had a chlorine coming off of it, right? So that is the mirror image. I think the next slide has actually got that guy in there, okay? That's the mirror image. This is called its enantiomer because it's its non-superimposable mirror image, okay? There it is right there. All right, now finally, another thing to do, so I just showed you one way to draw enantiomers would be to just draw the whole molecule exactly backwards. Another way would be to take all the chiral centers and draw them backwards. Let me go back to red here. So you can see that this is drawn as a wedge. So if you redraw the same molecule exactly the same, but you draw it as a hash, then you've drawn its enantiomer. Okay? So here, the enantiomer is, and you're going to be asked to do this on the exam, right? You're going to be asked to go to find all the stereocenters and just draw them backwards. So no stereocenters here. This has got 2 hydrogens on it. That's not an enantiomer, or that's not a chiral center. But here's a chiral center, right? So all I got to, that's the only one. So all I got to do is draw exactly the same thing and take my wedge and make it a hash. Okay? Now this is not a chiral compound. So you can't just always take every wedge and draw them backwards because that's not going to be legit. This is not chiral because this, let me go back to orange, it's got a hydrogen on it, right? So I'm going to go watch this square, circle, triangle. Wait, hairball and triangle are the same. So this is not chiral. All right, I think that's it. So practice, you need to get your models out. And you also need to practice drawing these structures. All right, good luck.